Hello, my name is Aban, and I'm going to be going over another project that I've made. Basically, it is a implementation of an HTTP server using C++ and the POSIX or Unix API. Um, so yeah, basically the goal was to learn how multi-threading works, and so this was a project that allowed me to do that. And so, as a high-level overview, basically what it is when you want to serve HTML files, there has to be a server application that actually handles the requests, and so that is what I've built. So it's designed for static file serving, and there's some performance considerations that I considered. And the architecture of this server at a high level is that it uses thread pools. Um, so basically, in a process, I'll just call this process like A. You can have multiple threads. And so what happens in this application specifically is that when you get an HTTP request, like a GET request, for example, for like, I don't know, index.html, the main thread will block until one of these workers is available, and then it'll just like send the task to a worker thread, which is called this worker. And then the worker will handle the client connection. And so the benefit of this is that you could have multiple clients at once. So you could have worker one, worker two, worker three, and so that way you can speed up like the responses, etc., etc. So I guess we'll just go into the code just to understand how it works. Starting at main.cpp, very simple. Um, this is a Unix thing, so that basically sockets, sometimes when they close connections, you get something called a sig pipe error, and it'll crash your whole program. So if you ignore it using Signal, then it won't do that. So the API for this is very simple. Um, you just declare your HTTP server service port and number of threads. If you just remove it, it'll still build, but it'll use the maximum amount of threads. So I'm running on an i7 9700F, which is an 8-core, 8-thread processor. So that would be 8 threads. Now, content directory, so kind of like Apache, you can declare a content directory where all of your content is. And so for me, it's www. So if I go and build where my executable is, this is where I store all of my content here. And then we can also set our directory index. So this is basically the default URL. So when you do um, a get with a slash, nothing else behind it, a get request like that, then this will be the default page. So basically, like when you go to a website, the default page is the directory index page. So that's that. And then there is also the option to bind error pages. So like for example, let's say you have like a 404 not found error, right? Like for example, the file doesn't exist. Now, you want to be able to serve a specific file, not something generic. So it supports that, and you can bind specific files for that case. And then you just initialize your service, and then you go from there. So the best way probably to look at it is just go from the top down inside. So to create this HTTP server, which was the first line, we have our port, we have our threads, port, and then we create our thread pool, which we'll talk about in a second. And we have our destructor. This just handles like the socket that accepts the connections from the clients. And so when we initialize our server, we create a socket. We use TCP, and it's pretty standard. And then we just set up some options here. So basically the purpose of these options is that you want to be able to reuse the IP as fast as possible, because there's like a cooldown apparently in Unix where like you can't use a certain IP address after the application is terminated for a certain amount of time. So this just makes it reusable instantly. And then we just declare our IP, and it creates an internet IP address, as you can see here. We create our port, and then we, all IP addresses that point to this machine will be accepting connections, basically. That's what this line does. So whenever you attempt to do a GET request to this machine from whatever IP, it will accept it. And then, yeah, there's not much else here that isn't fairly standard TCP setup. So, yeah. And then we start listening. So, due to the multi-threaded nature of this application, one of the things that we had to consider is race conditions. So, simple way to explain this is like, let's say you have like a, for example, like a, I don't know, like a coffee machine. So let's just draw like a mug, call this a coffee machine, right? And you have two people. Now imagine these people are threads, and the threads try to use the coffee machine at the same time. That would be a pretty bad mess, right? So in the same way, we have to prevent these race conditions with the access to the standard cout buffer or stream. So that's just your printing stream. So you have to use this primitive called osync stream, which uses internal mutex to handle that. And then, yeah, so then we have our main loop here. So this basically is the accept loop, and it just looks out for clients. So when you send a request, the main thread, it'll wait for your request with the accept function here, which blocks until it finds the request. And then our thread pool, we post a task for our thread pool so that one of the workers in the thread pool can handle that client. And so in that way, we are not blocked, and we can continue to accept more clients as the thread pool fills up. And so I think this would be a good time to understand like the thread pool itself, because, you know, before we go any further. So thread pool, simple idea is that you have like a big collection of threads. Threads are just like parts of the CPU that can run individual tasks independently. And you have a collection of threads that can each handle a task. And so as you can see here, the way ours is organized is that you have a queue. So a queue is basically first in, first out data structure where you can post the tasks into it. And so the first task that is posted is the first task that will be finished. And then we have a collection of our workers that will pull tasks from the jobs queue. And I guess looking at the implementation of this, yeah, so we create our workers, pretty simple. And we have a function called thread main. Thread main is basically the function that waits for a task to be available, and when it finds a task, it'll start it up. And in thread main, we can see that happening. So basically what we first do is we first lock our pool mutex, because we or not our pool, well, our pool mutex, which is protecting the thread pool's job list or like task queue. And this is because we're going to do an operation. We're going to do a write operation on that queue. So we got to make sure that nothing else is writing at the same time, or you could have some memory corruption, something could go wrong, etc., etc. And so once we've acquired our task pool, we use something called a condition variable over here, standard condition variable. And so the point, and we wait until there is, let's see. So we wait for a job, or we wait until the program has to terminate. So basically, the point of this is, first of all, we don't want to do something when there's nothing to do. And second of all, the purpose of a condition variable is that it makes sure that the thread is not being used, that it's idle and it's not consuming resources while it is waiting for a task. And so it's something internal, and it just helps with the performance, I guess, of an application, so that it's not like 100% usage or whatever. So yeah, we block until, or the thread blocks until it finds a task, and it also double checks to make sure that we're not like, ending the program or there's nothing left to do. And then if there's a task, then we take the first job available, and then we pop it, and we actually execute that task. And there's helper functions for posting tasks, which we'll see how they're used in a second. And then we just destroy the thread pool. Basically, the cv.notify all, this wakes up all of the threads so that they're not sleeping forever, that they actually hit this condition here, and they break out of their responsibility, and then they just join in the end. So back to the HTTP server. So the task is posted when we receive an HTTP request, And then the specific task that we're doing is the handle request task. So we just log that we have a new connection here, and now we are going to actually build our understanding of what the client is asking for. So we have a request buffer, and what we basically do is we just make a loop out of the read function or the receive function, and we just receive until we hit a delimiter. Now this delimiter, basically HTTP requests, every line ends in a carriage return and a new line. And at the end of the header for HTTP, if you look up HTTP headers, if there's like a source example, we could just find one here. So, yeah, basically this part, and then there's like the body. So we want the header because we're only doing GET requests because we're serving static files. So there's two /r's and /n's. It's called it's like a terminator. It's a very standardized thing. So at the end of the request header, there's always a guaranteed one of these things. So we just wait for that, and then we form our request. So once we have a request, we have this utility struct here called HTTP request. It has the request methods that are supported are get and bad. Bad just means it's like a malformed request and we don't know what's going on. And so we just parse the first line because that's all we really need to do for a GET request. Pretty simple stuff using standard string stream. And then we know what we want to do. We know what files we want to get, so we can analyze it in the response part of the HTTP server. So in dispatch response, it creates a response. So HTTP response, we have a response code, you have a content type. The supported content types for this web server project are HTML, text, CSS, and PNGs, and we'll demonstrate that in a bit. So we have response code, okay, bad request, not found, forbidden, unsupported MIME type, which is like media, an internal server error if something goes wrong. And then we have our content type, and then we have a variant for the body. So we'll see why this is a little important, but basically we can either send a string for like simple text files, or we could send an entire file descriptor. And for Unix systems, there's a function called sendFile, which makes sending files more efficient over the network by preventing copies, and we'll see how that works in a second. So here, back in dispatch response, so we switch on the request method. If it's like the get method, then we do an HTTP get, which is a separate function. Otherwise, we just create a response using these inline initializers. And the response code would be bad request because we have no idea what's going on, and then the text content type, and then we just send a string using advantage of variant in C++. So let's just dive into HTTP GET because that's where the juice is. So in HTTP GET, the way GET requests work is that you want to get a resource like on your server's like local directory, right? You want to get a file, you want to get an image, you want to get, if it was an API, maybe like some data from a database. So this, so the content root that you define in main.cpp is basically the content root, and we make sure that it's process relative. Then we define our index page. This is again defined in main.cpp. That's the index.html that you want it to point to. And for file directory, content root, resource URL. So yeah, in an HTTP GET request, there is a URL. So let's just see if we can get AI to generate. Yeah, so as you can see, we have a resource locator. And so we just make sure that we have that beforehand in case we need to return that file. And we just, okay, and then this thing is to get rid of a slash because in Linux or in Unix, Slashes are actually uh, the marker for an absolute file path, which means like it'll start from the root of the system, which is something that we don't want to happen. So if it's, the right size, then we get rid of that first slash. And so there's a couple case scenarios that we have to handle for the GET request. So the first type is that we get a request for the default page, which is the directory index.html, which is usually what you set it to. And that's just represented by a get slash and pretty simple stuff. So we just check if it exists using a standard file system. And then we create our file descriptor, fd open the this specific file. And we just do the standard error checking. If something doesn't open, then we just generate an internal server error. Otherwise, we generate our response, and we assign the FD of the file to our HTTP response, and we'll see how that plays out in a second. Now, case 2 is we have to retrieve a file that isn't the directory index. And so, first of all, we make sure it's not the directory index. Then we make sure that this actually exists, this file exists. And then we check if the path is safe. Now, the reason why we need to check if the path is safe is because of redirection attacks. Now, essentially how it works is, if we go back here, basically, way to redirection attacks work is when you cd, right? When you do the cd command in a terminal and you put 2 dots, it'll jump you out of your current folder up a folder. So the reason this is a problem for web servers is because when you send a GET request and if you have 2 dots in the file path, all of a sudden you have given your client access to the folder outside of the working directory of the server. Now, what's in that folder? Who knows? It might be your passwords, it could be your secret pictures, I don't know, something. So we need to prevent those from happening, right, to keep the server secure. And so the way we do that is file system canonicalization. So the standard library for C++ has a good tool for that called weakly canonical. And basically we check for a mismatch or the way it works is we make sure that the base and or the working directory of the application, the server, is the same as the directory same as the base directory of the actual file we're trying to access. And so we use a standard function here called mismatch, which basically checks for those mismatches. So for example, let's say we have a folder structure. We have a folder called apps, and then we have a server, and I don't know, we have index.html. And then, I don't know, let's just say we have secret.txt, right, that we don't want to share. So the way this would look as if you wanted to do a directory traversal attack and access secret.txt, you could just be get, assuming this is the working directory here where index.html is. Let's just add slashes here to make it sense. So we could just be get dot slash and then secret.txt, and we would suddenly be able to access that, right? So with the canonical, basically it simplifies these and it gets rid of them. So now all of a sudden the directory is apps and secret.txt. And so what we do basically is we compare the working directory of the server, right? So the working directory of the server is apps/server. And so we see that apps lines up, right? These two are lined up, but then all of a sudden these aren't lined up, and this part must be in the URL. If it isn't, then something is suspicious is happening. So in that case, we send a 403 forbidden, which is one of the supported error codes. Anyway, back to HTTP server. But if that doesn't happen, if it's a perfectly valid file, then we just make sure that we can open the file, and then we get the file type. We just use some string parsing to basically look at the last, or we don't use string parsing, there's actually a standard library feature where standard file system has a function called extension for standard path, and you can use that to get the file type. and then we just get it. And so if the file type is a supported file type, then we send it because not all file types are supported, as we talked about before. If something went wrong with opening the file, we send an internal server error. Otherwise, we send an unsupported file type, basically. And then this was the directory redirection prevention thing that we were talking about with the 403 forbidden. And then if it's not findable, if this file just does not exist, then we return a 404 error. So pretty cool stuff. Anyway, so that is how the GET request works. I guess, and then for error pages, since we're talking about 404 errors, we have the support. We have the option to support user-defined error pages, but otherwise, the way this works is that we can just sort of create a default error page that just sends a text response back, and we just use like the name. So like if it was a 404, it would be 404 not found. If it was a 403, it would be 403 forbidden. It would just send that plain text, and we'll see that in a second when I actually demo. So that's how the GET request works. So once we've formed our HTTP response, now we need to actually get to sending that response. And this is where some of the funny Unix stuff happens, where we can like optimize the speed of our server. So in dispatch response, we were here, HTTP GET. So once we're done constructing the response, we construct the head of the response as a standard string, and we send it. Now, this capital S send is just a function that wraps around the regular Unix send, but it makes sure that all the bytes are sent because the Unix send doesn't guarantee all bytes are sent, so it's just like a loop around that. And then over here, we have a visitor. Now, remember this variant that we had in HTTP util. Basically, our HTTP response can either have a string as the body or a file as the body. And so we need to be able to either send a string or a file. So if we send a string, great. We just use that same send function from before. Now if we send a file, we're going to use a special function called send file, and we're going to close the file descriptor. And the reason we have a distinction here is because of the send file function here. Now the Unix send file function basically allows you to prevent the amount of copies that occur in a between the buffer that's the file and getting the actual bytes sent. So it's like it does everything in kernel space or something like that. So it saves a lot more copies, a lot more reads, and makes it overall a little quicker because copies are expensive and allocating memory is expensive. So yeah, and then that's like how we serve the files, and overall that's pretty much how the gist of the server works. We just send those, and then that's the end of the task. And then we just close the connection, and that's that. Now on to some of the more interesting details. Let's see. So we talked about performance. Alright, so let's just demo this real quick because why not? So we're going to run it. Okay, let's just run that. Okay, so started listening on port 8080. So I'm going to just head over to localhost. So give me 1 second. Anyway, so yeah, we're on localhost 8080, and this is a simple page that is generated by ChatGPT because I don't really know how to write HTML. Very simple stuff. So as you can see, this is our directory index that we have defined in our index.html. If we type in index.html, it's the same page, right? Now, let's say we're trying to do a 404 error, right? We're trying to access something like Gooby. Then we get a 404 not found, and the server internally knows that it can't find this file, so okay, we're going to return a 404. Let's see what else we can demo. Bad request, that would just happen if you happen to send something weird. We can try, oh yeah, so image support, obviously it's not just HTML that we support images as well. And so when I was using the standard C++ file functions instead of the Unix file functions, you had to actually consider that images must be set in binary, otherwise it'll corrupt the image. So there's like an image demo page. Um, and yeah, we can serve all these different files. Now, it's hard to demo the 403 because modern web browsers prevent against these attacks, so we can try using curl with path as is. So let's see here. So curl basically allows you to pull the actual file. So curl dash dash path as is. And then we can just do localhost 8080. And then we can just do that. And then you can see we get our actual, if we look at the HTML that we get, we can see that it has like that lock icon that's found in the 403 page, access forbidden. So you can see that directory traversal attempt was prevented successfully. Okay. So yeah, overall, very simple, like from the surface, but very deep on the inside. A lot of considerations. And so we did benchmark, or I did benchmark this server using the work tool. Work is like a modern HTTP benchmarking tool for web servers. And I forgot how the syntax goes, but work. It's like you could set, so yeah, so work, you could set the number of threads. So right now, I think I'm using all 8 threads on the server, but we'll just put 4 anyway. It'll just do whatever it needs to inside. And we can just define the number of connections. So connections, let's just do like 400 connections. And then for the amount of time that we want, we could do, you know, maybe 10 seconds. And then HTTP and like that. So we'll just do a request on the index.html page right here. And you can see it's getting all these connections, and so it's stress testing the server with about 400 connections for 10 seconds straight. So while we wait for this, so our server successfully handled 57,000 requests across all threads, no connection errors. These read errors are because of HTTP keep alive, so I didn't implement that, so that's why we have that. Total 2 gigabytes transmitted in these 10 seconds, so it's, you know, pushing the data through with an average latency of 6 milliseconds, which is pretty good. And so yeah, everything works pretty splendidly. I personally tested it with 4 cores on so the server was running on 4 cores with 600 connections, and it handled 63,247 requests. Right now it's running on 8 cores, which is probably why it's much closer. But and it had an 8.4 millisecond average latency. Again, it's a little lower because I was running on 4 cores. And you know, it's pretty stable. There's no errors happening on the server. Server isn't crashing. If I go back and if I try to connect to localhost again, perhaps something went wrong. But let's see. Yeah, I don't know. Anyway, some weird stuff. But yeah, point is it works. So it works well enough for testing and benchmarking, etc., etc. So yeah, overall, that's how this project works, and yeah, pretty splendid, pretty nice, and learned a lot. So very cool. Thank you.